Hi, Professor. I'm from Geek Squad team. I'm Ruchita Reddy Kulguri. My teammates are Suresh, Vinay, and Hashavardhan. Now, I'm going to present about a midterm numeric project, which is about predicting the house market trends in the California. Here, our project tells about the California housing market, leveraging a multi-facet data science approach to forecast the housing prices and pinpoint the investment worthy properties. The analysis integrates three distinct datasets encompassing the property attributes, the crime rates, educational infrastructure, proximity, and the box score, like to create an enriched dataset offering a holistic view of all the factors influencing the property values, employing a suite of machine learning models including the random forest, gradient boosting, fractal clustering, etc. We'll discuss about it further in this collab. And it We have written a detailed write-up of this project in this document, which is uploaded in the shared drive. Now let's look at the data sets. Here first we have imported all the necessary libraries. Then the first data set here we have the important columns such as like the median income and the median house value, ocean proximity, and like the total population, bedrooms, etc. And we perform the data cleaning and EDA and the steps. And we have also performed some visualizations. You can take a look at this correlation. Here, the correlation between all the columns, all the features are generated. One correlation, one means they have a good ratio. Like if suppose the longitude value increases, then the correlated value with it, for example, latitude, then it also increases proportionally. So if they have a good correlation between them, then the value will be 1. If, for example, let's take in the value of median income. The median income and the population is inversely proportional. So the correlation value is very less between them. And here are some of the box plots, like the histograms. And the second data set coming to it, we have scraped the data set which have very important features such as crime rates, violent crime rates, and the property crime rates. It is also uploaded in the shade drive. And we have amalgamated it with the first basic data set. So these two are the extra features we bought it from by scraping. And coming to the data set two, same we have performed all the data cleaning steps and the visualizations on it. And coming to the data set three, here we scrape this data set which contains the schools near me and other informations, and we amalgamated with the previous data set. Can take a look at the values which are amalgamated, the columns which are amalgamated. Like the cleaning data is performed already, and like some of the visualizations are done. We can take a look at the distributions of the total bedrooms with the frequency, and the distribution of total bedrooms is like it indicates the presence of the we can take a look at the graphs which have the outliers with high values. Given this, it's more appropriate to use a median to fill with the missing values. So we have used median to fill the missing values. And like after all the actions are performed, we can see that like there are no missing values in it. And next we perform the visualizations on dataset 1, 2, 3, the amalgamated one. Next, here we have performed the Gini score and the SHAP values too. Here we have trained a random forest model for the Guinea importance. Here, it is of a decision tree, like which is made used for classification. The Guinea score for in that decision tree will have a each box which is made with a node contains a decision based on one of the features of the data set, and it also has a branches and with a Guinea value in it, and the value tells about the it indicates the distribution of the samples. And after that, we found out that these are the top five base important features based on the Guinea score. Next, we'll take a look at the models, like we'll train the models and discuss about the models. And here are some of the plots related to the distributions. And coming to this, here we have amalgamated the datasets in the previous cells. Now let's work on it. Let's apply all the metrics on the amalgamated data. First, we'll take the data set 1 and we have performed the metrics such as accuracy, precision, recall, F1 score, and we have printed that in the form of table. And same with the data set 1 and 2, and same with data set 1, 2, 3, like the amalgamated one. Now let's print all the metrics here after and before the amalgamation so that we can just compare the performance of the model before and after adding new features, after adding new columns to the datasets by the amalgamation. Here we can take a look at these are the values for the dataset 1, dataset 2, and the dataset 3. The green indicates that we have styled that in a manner that green indicates that these are the highest values. We can take a look at the accuracy column. The highest one is for the amalgamated one, which contains three data sets. It has a good amount of features which helps us to predict the values correctly. So the accuracy is greater when compared to others. And the pink one indicates the least accurate, least values. You can take a look at the values. 0.8 is 88 is the least value among them. So for that, the color is printed as pink. And coming to the next one, here we are implementing the ML models to build and refine our data. We have performed the clustering. Here we have choose the hierarchical clustering, which seeks to build a hierarchy of clusters. It's an algorithm that groups the similar objects into groups that called clusters. Here the endpoint is a set of clusters where each cluster is distinct from each other and the object within each cluster are broadly similar to one another. And like how it works is the hierarchy clustering starts by treating each observation as a separate cluster. Then it repeatedly executes the following steps, such as the iterative process continues until all the clusters are merged together. This is called as agglomerative hierarchical clustering, which is a hierarchical clustering method which works in the opposite way. They're all device works in the opposite way. Okay, let's not discuss about them. We'll focus on this hierarchical clustering. Then next, after this, we have we have found the golden cluster and using the fractal distance calculation. For the k-means, we worked with the fractal distance and Euclidean distance too. Here, the fractal distance clustering is used to identify the patterns in the data set, like that may not be apparent through other the techniques. For instance, the model can be used to identify clusters of houses with similar pricing and features that may be located in different neighborhoods. This information can assist the real estate companies and investors in identifying the areas with a high potential property appreciation. We have written a function for the calculating the fractal distance. And next we worked on the k-means with the fractal distance. Here implementing this with a custom distance, which is the fractal distance is a custom distance. It involves modifying the traditional Euclidean distance calculation, which is part of the algorithm. K-means is inheritedly like designed around the concept of minimizing the variance, such as sum of squared Euclidean distance with clusters, which makes altering its distance metric non-trivial, especially with the algorithms optimized for speed, scalability, etc. Next, we have performed the clustering and the silhouette score and SSC is found out. And we can take a look at the graph, silhouette score after the k-means clustering. The silhouette score value decreases with the increase in the number of clusters. And next we found out the k-means with Euclidean distance. Here k-means clusters with Euclidean is the standard implementation of k-means, which is widely used by partitioning the dataset into k groups or k datasets based on the feature similarity. We have here is a below implementation with the Euclidean distance. And like we have plotted the graphs within the SSC after k-means clustering. And the silhouette score is, we found out the silhouette score. And next we have done the fractal clustering with the Euclidean distance. We have done few trials to get the results better. For the first trial, we have taken here, like we can see that within the cluster, we found out the SSC and the silhouette score. And after that, the score of 0.23 is we got it for silhouette and SSC of 86. Uh, uh, what does this represent means? A silhouette score of 1 is a perfect and which indicates that every point is exactly on the border of the nearest cluster. This usually happens in very distinct or well separated area. And like SSC within the cluster, here this value represents the sum of the square distances between each of the cluster and the cluster's centroid. The lower SSC value suggests that model has fewer errors and the clusters are tighter. So we believe uh, this is not bad. The value of SSC within the cluster is not bad, which suggests that the model has like very fewer errors and the clusters are tighter. But anyway, we want to improve the score, so we'll perform a second trial. And like in that, we found out the values for it. Here we have three rounds of it, 3 rounds of clusters, and we can say that 45 comes under the golden cluster because it dominates all the other two units. Next, we'll have the fractal clustering with fractal distance. And similarly, we found out the silhouette score, SSC values, and plot the graphs. And the first trial in this, in the first trial, we got the silhouette score as 0.3. And the next one with the clusters, we got 50 and 50. Here we can say that the golden cluster, we cannot identify the golden cluster. So let's take a look at the second trial. Here we have taken the indexes like the cluster number and the loops. We can change the maximum number of loops. And next, the same thing, the silhouette score and SSC is found out. And here we can identify that 29 is greater than 21. So we can say that the zeroth cluster is a golden cluster. Train and up, now let's train and apply the Muller law. Here we'll proceed by pre-processing the data, splitting the data into training and test sets, applying the 5 regression algorithms and evaluating their model's performance. We have taken these 5 regressors and like we have performed Muller loop on the first data set. And then next we have the results of them. Like the best algorithm for this is a random forest with the highest R to score and the root mean square error should be least. Among these values, random forest has least root mean square error value and the highest R2 score. So we consider this as the best till now. Let's take a look at more metrics on the other data sets. And we found the same. And like for the dataset 1 and 2, it's the same thing. Again, random forest gave us the best values with less errors. And when performed on the amalgamated dataset containing three datasets, we found the same thing that the R2 score is highest for the random forest, indicating that this is the best one. And like the random forest has the like lowest RMSE and the highest R2 score, which is considered as the best performance among the model listed. Like the lower root mean square error values indicates closer fit to the data, and the higher R2 score values indicates the model explaining the greater proportion of the variance. And we will perform the Muller loop classification. Here, we need to first transform the continuous target variable, which is the median household value, into a categorical one. Then, like the common way to do is dividing the houses values into categories low, medium, high on certain thresholds. Here we have taken few algorithms to perform the classification. For each model, again, we'll fit a training data with the transformed categorical target, making the predictions on the testing data and evaluating the performance using the metrics such as accuracy, precision, recall, F1 score. Let's begin by training and evaluating these models. And the similar Muller loop is performed on the dataset 1. And we have printed all the values of the respective classifiers in the table. And we can see that random forest gives the greatest accuracy among them. And coming to the Muller loop on dataset 1 and 2, like the amalgamated one, which contains 1 plus 2. And we have printed all those metrics here. And this also indicates that random forest is giving the better accuracy, better performance. Let's take a look at dataset 1, 2, 3, the amalgamated one. And the same here, we got the greatest accuracy for the random forest. Now we have taken the latent variables. Here we have taken the latent variables such as the natural walkability index to enhance the our model's predictive power. Here we can take a look at the latent data set, which contains all the values, and the natural walkability index is here. In our pursuit of refining and enhancing the predictive capabilities of machine learning models, we have taken these latent variables and manifolds. Like, let's discuss like what's the use of it first. Like these constructs enable us to capture the underlying and often hidden structures within our data, offering a deeper understanding of the factors influencing the housing prices in California. Like this part outlines our approach to integrating the latent variables into our analysis, detailing their selection and the derivation impact on the model performance. These variables that are not directly observed but are rather inferred through the model from other variables that are observed directly measured. These variables can like encapsulate complex and underlying processes that influence observed variables in significant ways. Here, the natural walkability index as a proxy for neighborhood desirability and environmental quality. We engineered a latent variable The natural walkability index, this index combines various features such as proximity to parks, walkability scores, and the local amenities, offering like the great composite measure of neighborhood appeal. And like we have also taken the other latent variable. We'll discuss about it next. Then we have done the Muller loop on the classification part, Muller loop classification on this data after adding the latent variables to the data set one. And then we performed like the values are printed here for all the classifiers. And the regression is also performed on it by taking 5 regression algorithms, and those respective metrics are printed here. And next, coming to the data set 2 plus the latent variables. Here, our data set 2 contains some of the important properties such as crime rate, violent crime rate, property crime rate. And like adding these latent variables to the data set adds much value in the model's performance. And similarly, we have done the Muller loop classification and the regression. Like the another important latent variable is the economic condition score. Here, like leveraging these economic indicators such as employment rates, median income, business growth, we derived a score reflecting the local economic conditions, like hypothesized to influence, sorry, influence the housing demand and prices. And again, the regression is performed on it. And like we have added the latent variables to the dataset tree and checked the classification and regression performances here. And then next we have printed uh, all the classifiers metrics in a table. Like this is for the first data frame, and second data frame, and the third. And like combinedly we have printed all the data sets, sorry, all the classifiers metrics in one table. And here again the green represents the highest values, and the pink line represents the lowest values. We can look at the good performer or the good classifier, which is again the random forest, which gave a great accuracy. And like these are from the data set 1, and from the data set 2, even the random forest is highest performer, the greatest performer. And similarly here, and the least performance is given by the SVC in all the data sets. This is for the classification part. And let's look at the results of the regression part. We have printed all the regression parts separately, and like we have printed in a table to compare it. Yeah. Next, we are creating and saving the best performing model. Here, best performing model is a random forest classifier. So we have created it in the pickle file so that we don't need to train it again and again. Simply, we can just load the saved model. And similarly with the regression, we have done the same thing. In the regression, the random forest regressor is a model which gave the greatest accuracy. And this is about a project, and let's take a look at a paper, IEEE paper. Coming to the work division, uh, myself and Suresh worked on data scraping part of getting the data of the property crime values and the volume crime values and the walk score latent variables data sets. And we have performed the EDA visualizations and the cleaning part on all the data sets. And these amalgamations are done by the Harsha, Vardhan, and Vinay. And then myself and Suresh worked on the Gini score sharp values calculation. Then I been worked on training the models and like checking the metrics and the accuracy. And like we have performed some of the feature data preparation and the data preparation with the feature transformation, plotting the distribution of key variables, plotting the relationship between median income, house value, plotting the correlation matrix. We have performed all these. Suresh worked on plotting these distributions, and then I worked on amalgamating them and printing all the metrics for the amalgamated data and for the individual data. Then I've performed finding the fractal distance calculation, k-means, fractal distance, and Euclidean distance. I have worked on it. Suresh worked on the hierarchical clustering part for and printing the performing the clustering. Next, we have worked on the apply algorithms and Muller loop. Harshavardhan and Vinay worked on Muller loop on the regression and the classification. And coming to the latent variables manifolds, Suresh and myself worked on it combinedly. And have worked on displaying the metrics into the table format. And I have worked on saving the pickle files. That's it. Let's take a look at the IEEE paper. Here we have entered all the format and all the things we have mentioned, some of them in the collab. And first we can take a look at the abstract, like which tells about the California housing market, the analysis integrates the project data sets encompassing the property attributes, crime, etc. Like the summary is it mentioned in the abstract, and we have a great introduction about the investors ideas and like what it attracts the investors for the project. Next, the data narrative and the proximity to educational infrastructure. And like we have given us some details about the crime rates, and let's perform some of the cleaning EDA. And then the methodology, which contains the data pre-processing, feature engineering part. And like the machine learning models for predictive analysis, we have mentioned about the models, the training and the evaluation part, and comparative analysis and the model interpretation. And about the EDA part, like we have done the visualization such as the heat maps, box plots, scatter plots. Then, oh yeah, you can take a look at these plots here as well as in the collab. And like we have implemented the algorithms and found the golden cluster with the help of the fractal clustering with the fractal distance, and mentioned about the Muller loop, the latent variables, what are those variables and what's the use of adding them into our data set. And finally, the performance metrics of all the classifiers and of all the regressors are mentioned. And like we have also mentioned about the future scope, while our study provides a great foundation for understanding the and predicting the housing prices, the nature of real estate dynamics presents avenues for further research for like data enrichment and the temporal analysis and the technological advancements, such as exploring the emerging machine learning techniques such as deep learning neural networks, could uncover the deeper insights to improve the predictive accuracy. And like incorporating additional data sets such as environmental sustainability indices. Currently, we have added the crime rate, walk score, and some other ocean proximity, median house value. And like these are some of the important features, but like we can add some more of them which related to the environmental sustainability indices, traffic patterns, demographic shifts, like could further refine the predictive models. And like one of our other good feature is the walk score, so that like people buying or the investing in them can take a look at the walk score, and then the crime rate. So all these features are very helpful for them in picking the house. Yeah. And these are references. Thank you.